Hey everybody, sorry we're a little bit late there. Just 2 minutes late or 3 minutes late. It's all right. We got Madison's got a question. Kayla, good to see you here. Can you do the question from chapter 13 homework? Suppose the budget has the support of blank percent of the voters. What is the probability that the newspaper sample will lead to predicting a defeat? That's a great one. Kayla has a question too. Do we need to mention exactly what we are interpreting since there are no graphs? Using a linear model, the examination of demand by yes. Do we need to say otherwise identical? Yes. When interpreting, oh no. So for the p-values for the linearity test, so really quickly on Kayla's question right here. So let's hop over to that. I was closing everything down because I've got about a billion things open right now. It's pretty crazy. I was grading all the take homes last night. Got to make sure everything's correct. I'll be sending out an email at 3:20. Sorry, I'm half asleep. I'm like, oh my gosh, got everything graded, and then had to close down a bunch of stuff. Because I was doing a whole bunch of like, can I show this? Make exam grades. Yeah, it's the file that makes your exam grade is 1,185 lines of code. And then Madison, we're gonna do your question here in 1 minute. So I'll answer Kayla's question, then we're gonna do Madison's. And Kayla's question looks to be quick. So Madison, hang in there. We got this. I'm off the screen. Let's go to the main screen. Now, obviously, I didn't write this all last night. I didn't write 1,185 lines of code last night. My head would have exploded, but no. So there's all the lines of code going through, finding all the answers to everybody's assignment. We got the different histogram of results right here. Here's how the results look. Very, very, very left skew distribution. I've contacted a few people. We've figured out kind of what's wrong. I'll be sending out an email. You might have seen your grade appear. So very, very quick thing to 3:20. You might have seen your grade appear, and then I might have hit it because I want to make sure, because I got quite a few emails and I was staying up. Yeah, anyways. But if you did fall in this kind of range that, is lower than you probably wanted to get, please reach out to me. Or even if you missed one, reach out to me. I do have a way of creating the answers. So I can create the answers. I can show you the answers. You can check your work. So Kayla, especially if you want to send me an email and say like, I don't know if you saw your grade. I think yours was probably posted for vet. But if you want to say like, hey, Brian, can you send me my answers? And I can see what I missed. And I can see the right answer. And I can see the code for it. I can send you that. And so all you have to do is just say, send me my answers. And then I'll do that. I'll send out an email announcement about that. And I'll unblank the grades. A few people have already had their grade changed because like one person misentered their ID by one number. So if you misenter your ID, it drastically changes it. So yeah, it's email me and I can send you yours. And I think it was posted probably Knoxville time about between 1 and 2 a.m. And I stayed up till like 2:30 here. Anyways, I'm losing my mind. Let's go back to here. Okay, so Kayla's question, when you do the check regression on this, we've got some multiple models in here. Let's go down to this multiple model. I don't love that multiple model. Demand not found. Let's fix that. Let's run all this up here. There we go. Now we got some demand. This is when you'll say two otherwise identical. Got a bunch of interesting p-value configurations there. This is when you'll say otherwise identical, Kayla, with these things right here, like when interpreting average temperature. But if you're doing something like the check regression, you won't say two otherwise identical. It's just the linearity for that one. Does that make sense, Kayla? And then we're going to do Madison's question here in 1 minute. But does that make sense, Kayla? You will, for here, you would not say otherwise identical because these are just checking the linearity conditions. And I do have some categorical variables which can't be checked for linearity. But here, you would say here you would not say are otherwise identical. Here you're just checking the linearity. Or for these right here, there's the linearity of the overall model, which cannot be checked. There's the equal spread and normality. But for these, this is the summary command. The summary command is interpreting coefficients of either the intercept or other coefficients in the model. Here is where we say are otherwise identical, which I think is the last question on the assignment. The whole is otherwise identical. So it kind of gives away some answer right here. 2 days where we are selling bikes that are otherwise identical but differ in their average temperature by 1 degree Celsius are expected to differ in their bike demand by -341, where the day that has a higher average temperature is expected to have a lower bike demand. If there is a p-value for the overall model, if there is a p-value, you can discuss it for the overall model. And so this is the p-value for the linearity of the overall model. It's under the linearity for the overall model. And the p-value for the overall model here is going to be this one. And this is the significance of the overall model. Does the model significantly reduce the sums of squares? So each p-value, and as I try to highlight this in 201, especially later in the semester, so 201, important stuff right here, each p-value is dependent on the test you are doing. That p-value is the significance of the overall model. Kind of the easy way to understand it. The deeper way is, does our model reduce the sums of squares in a significant way that is unlikely due to random chance? And the answer is yes, because that is statistically significant. The p-value down here for something like the linearity, like if this was, we did have a 0.366 right there, says that is the observation of the linearity we see likely due to random chance? Well, assuming that linearity is true, and the answer is yes for this one, we can't perform the other test, but the linear relationship between average wind speed and demand looks to be like what we see is likely linear. The differences from linearity are probably just due to random chance. So there's not statistically significant difference from linearity because the null for that is linearity. So you always have to think about which test you're doing because these are check regression tests and the null is that it's good, linearity is good. That's like a basic way of understanding it. And we do not have enough evidence to reject the null. We continue to believe the null. We're like, well, it's probably linear. I mean, maybe it's got a little bit of, like all this in the background right here. You say, man, maybe that's just a little bit of, it doesn't follow it perfectly. Well, that's got it for great questions, Kayla, right there. I'm going to hop over here to 201. We're 10 minutes in or 7 minutes in. Thank you so much. I think it was Madison, I think. Madison, we are doing some 201. I'm pulling it up right now. I meant to spend like 2 minutes on that, but I want to answer everyone's question. This is a big one. This is a really great question here. This is a tricky one. This is chapter 13 due tomorrow night. Tomorrow. Here it is. This is not going to be it yet. Chapter 13. This is a tough one. So this one right here. Awesome. Lastly, when you answer yes or no for the it was the very first one you asked. Do we need to mention exactly what we're interpreting since there are no graphics? Yeah, you could do that. If you want to send me your interpretation, I would try to be as think about just writing a good report. You can always debate your grade. Like if you think you should have more points, you can always be like, Brian, I thought if I did this, I'd get full points. And I'd be like, yeah, sure. Yeah, I would try to be as explicit as possible with what I'm stating and making it clear. And it is hard to get graphics in multiple regression due to it's just hard to graph this kind of stuff. You can't, with 20 variables, you can't really graph stuff sometimes. Like it doesn't make a nice graphic. But yeah, and always feel free. If you get points off, a few students have emailed me on pretty much most assignments, and I do not mind that. And it's kind of like to get points back half the time. Half the time I look at it and say, yeah, you should get some points back. And the half the time I look at it, I'm like, nah, I agree with the grader. and 201's also emailed me and said, hey, Brian, I was a decimal place off here. And I'm like, yeah, let's give you the point back. Let's give you the points. I try to be as fair as possible. I try to make the same decisions. So for decimal errors, I always give points back in 201. Like if the answer to this question was, well, this one is going to be a decimal. Let's say the answer to this one is this, and you put something like this right here, then I would give you the points if your answer is that. Let me add some points to the viewers. Mubot should be awake. Mubot is awake. 100 points to the viewers. That is not the answer to this question. Let's do this. Here we go, Madison. Time for this question. Just before a referendum on a school budget, a local newspaper polls that many people. And good, I got this close down. They poll this many people. They poll 389 people. And they want to see if people are going to vote for the budget. Now, the budget actually has the support of 54% of people. The budget actually has that. I know it doesn't say actually, though, there, but that is important to understand that we're saying this is the truth. And that is so key for this problem that this is the truth, that when we put this into here, we should know the notation. What is the notation for the truth? So if you're following along right now, because this is a really tough one, this is probably one of the toughest ones for this chapter. What is the notation for the truth? I'll do the easy one. So, Brian, that's the easy one. We know what that is. That's sample size. That is the sample size, which is n right there. But the other one is the truth. It is what percent of people are actually going to vote on the budget. Now, this question is weird theoretically. So that, yep, and that's going to be the truth, and that is P right there. Now, great job, Madison. And so what's weird about this problem is they actually know this. Now, they probably wouldn't know this. It should say like unbeknownst to them, but the true proportion who will vote on this budget is 0.54. Because it's like, how would you actually know that? And it's like, okay, this is like a theoretical statistical question, because we wouldn't actually know this. But when election day happens, 54% of people are going to vote for this. But if we were to talk to, let's say, 2 people, and so we go out and say, a sample size of 2, would you agree that we'll either see in the sample only one of these 3 possibilities? We'll either see 0% vote for it, we'll see 50% vote for it, or we'll see 100%. Because we talked to 2 people. We're just saying we go out and we take a sample size of 2 people, and we say, are you going to vote for the budget? If no one says yes, then 0% said yes. If one person says yes, then 50%. And if 2 people say yes, then 100%. So when you think about this, here's what's going to really just hurt your head for a moment. Awesome job, Madison. So there's the part that's just like, wait, what? Okay, no matter what, no matter how many people we talk to, what percent of people, now don't look at that too much. No matter how many people we talk to, what percent of people would you expect to vote for this budget? Like if you talk to 1 million people, or you talk to 20 people, or you talk to 30 people. So that's kind of a tip right there. Like, what percent of people would you expect to vote for the budget, since you know 54% of people are going to vote for it? You know that is the truth. So if you were to talk to 40 people, 20 people, 30 people, what percent would you expect to vote for the budget? Be careful. I tricked you with this right here. So it would be 54%. 54%. In this example, it does seem likely that 1% or 50% would vote for it. And plus, you can't get 54% with some numbers. But if 54% of people are going to vote for this budget, then we would expect to see 54% on average in the long run. And mathematical proof, the word suppose indicates that the falls is distributed. Oh, you're right, Kayla. Let's throw some 50 points. Kayla helping out the mathematical lingo right here. And what we're actually doing right here is the law of large numbers, because we're not saying, and here's what's interesting. So that's mathematical, like saying this is taken as truth right here, like take this as a true statement. So yeah, see, I'm glad I didn't know that, Kayla, till this semester. I'm not even joking. That helps expand my knowledge. So I can later, I'll be saying that for semesters to come, hopefully. Like, the suppose is actually used in mathematics to denote that this is true for the situation. So yeah, they're telling you this is true. See, statisticians don't say that. I'd rather just say it is true. Darn you, my Pearson, with your mathematics. If you were to repeatedly do this over and over again, in the long run, you would see, and this is like with repeated trials of 2 individuals, the binomial distribution would be a little bit odd here. You would see 54%. In the long run, this would average to. And this would be the what of repeated trials. Now, just we're doing theoretically for a moment. This would be the what. Like if you said in the long run, this would average to this, which that's the answer. In the long run, if you kept taking 2 observations, 2 observations, 2 observations, 2 observations, 2 observations, and finding out what percent, if you kept doing this, because sometimes it would be this, sometimes it would be this, sometimes it would be this, it'd probably be 50% a lot more. So you're going to see a lot of 50%, you'd see some of this, but you would do this repeatedly, and repeatedly doing this, you would see an average of this. So what does this make this right here? That makes that the mean for the distribution of the sample proportion, because we're taking a sample proportion right here, and then we're finding the mean of it. And so that's the mean for the distribution of the sample proportion, is that is equal to P. So the mean for the distribution of the sample proportion is equal to P, because it's saying in the long run, when you take samples, on average, you would observe the truth. So this is the on average portion of it. In a sample, you would observe the truth. So listen to it again. On average, in a sample proportion, you will observe the truth. On average, like if you did it repeatedly, kept taking samples of 2. Now, we're not taking samples of 2 right here. We are taking samples of 389, but the rule still applies, and on the long run, we will observe this. Now, the other formula, I wish I could explain to you better mathematically than here's the answer for what it is, but we're just going to say it that way. The other formula, and Kayla, if you have any statistical theory knowledge on this one, I would gladly accept it, because this one is P times Q over N square root, and it just works. It is the standard deviation for the distribution of the sample proportion, and I'm sure there's some statistical theories that show it, but standard deviation, like standard error, is variation, and this is the variation we would expect to see in a sample proportion. A lot of crossover between 320 and 201. That's just variation in the sample proportion. Now, the classic question people always ask if you're ever here, please ask it, because usually people ask it one time, they're like, oh, I know it now. The classic question people ask is, what is Q? So when it comes down to what is Q, Q and P are complements. So just so you can see, P and Q are complements. If P is 0.54, you just take 1 minus that. So you go 1 minus 0.54, and there you go. P and Q are complements, which mean they add up to 1. So you're also reviewing probability or mathematical probabilities by doing this. And we see right here, just they add up to 1. Good stuff. So make sure your 2 add up to 1, and you've got it. So what we're going to do now is we're going to do P times Q over N square root. Let's do that. P times Q over N. N is sample size, square root. And we've now found the mean and the standard deviation for the distribution. That's equals... And I always like to carry out all my numbers. I'm just going to put this in right here for now. But the whole point of this, we're going to go over to Mr. David M. Lane's website. The whole point of this is to draw the distribution. So we're going to use the normal curve here. And we need to meet the conditions of random. We've randomly selected these people. Less than 10%. So we can't live in a really small town. These have to be less than 10% of all individuals. And then we have to have at least 10 successes and at least 10 failures. It's basically a 50-50 split. So we should have like 200 successes and 200 failures. Not exactly, but we're going to have a lot of successes and a lot of failures for this one. So we go here, we put in the mean of that. We put in the standard deviation, which we did not copy today. Copy. There we go. And now here's the confusing part for people. If this budget was predicted to lose and be defeated, it would get less than what percent of the vote in the sample? If this budget was predicted to be defeated, it would get less than what percent of vote in the sample? If this budget was predicted to be defeated, it would get less than what percent of the vote in the sample? So if this budget were to be predicted to get defeated, it would get less than what percent of the vote in the sample? And this is where usually people get stuck. They're like, wait, how am I supposed to figure this part out? How do I figure out if it's predicted to be defeated? So if the budget were predicted to be defeated, it would get less than what percent of the vote in the sample? I think it's because I have the cursor up there. Less than 50%. Lydia, great job. Let's throw some 50 points out there. Everyone working hard today. So we're saying in a sample that we took right here, is it possible... You're fine, Kayla. I was talking about if you know more mathematical theory, please tell us. I want us to look at the z-score right here. That's an estimate of the z-score. We could always do observation minus mean over standard deviation. And that's going to give us the exact z-score, which is going to be like, ooh, it's going to be a little lower than that, right? It's going to be about here-ish. It's going to be like 1.4. So let's find out the z-score. So we can do observation minus mean over standard deviation, 0.158, negative 158. That's about right. That is the z-score of it. And you can see the z-score here. Really? Yeah. There go. 0, negative 1, negative 2, negative 3. 1, 2, 3. There we go. And so what percent of area is that? Negative 1.58. Let's think about this. Brian's going to guess the answer. I've got a few guesses here. Let me slow down my mind. Okay, I got to guess. Round to 3 decimal places. Oh, wait, that's wrong. I forgot my 0. Oh, we didn't get it. That should be around here. There we go. Okay, so I was guessing using the empirical rule and the numbers I know, but let's view the exact answer. You need to go to the David M. Lane applet, which we do have in the chat right now. I'm going to have MuBot say it again, just in case you haven't seen it. Using the David M. Lane applet, we can go below 50% because we're saying the vote gets less than 50%, and it rounds to 0.057. I had to think a little bit higher, a little bit lower, and I was like, I don't know. So I'm using numbers on the empirical rule that I know that I can use repeatedly to find z-scores. And yes, you can also use the z-score we calculated by going here and going below negative 1.58. And you should get the same number. Yes, it's just we carried out more decimals if we do this. So there we go, and we get the same answer. Please note this is the same answer. In this version, we are using the z-score right here, which was found by taking observation, which is 0.50. This is the observed p hat right here. Let's put the notation below this so people can see how to get a z-score. The notation for this, I'll put in red, will be p hat, which is observation, minus mean over, and the standard deviation was p times q over n square root, and that was equal to the z-score. So this is p hat minus p over p times q over n square root. So the p hat right here is 50%, because why 50%? Well, or 0.50. Let's do that. Because we're looking at the probability it would be predicted to be defeated in this sample. So what is the probability of a sample obtaining a proportion less than 50%, which means we would predict defeat? So what is the probability in this sample? Ah, awesome, Madison. Hopefully people understand this theoretical. I mean, sometimes I could just solve the problem and just be like, here's all the answers. But I want people to understand the theory behind this that we're looking at. What's the probability that a sample we take would show that it would be defeated given the truth is 54%? And it would happen about 6% of the time, or 5.7% of the time. Lydia, everyone, what questions do you have? We could do who wants to do a speed run of a chapter? You can pick a chapter. I'm going to try to break these videos apart and do speed runs. Do you want to do a speed run? Yes, D-Scaff right there. I did a speed run. Do you want to do one today? Do you have a chapter you want? You can pick the chapter. You can say, Brian, do a speed run of this chapter, and I will do a speed run of the chapter. You won't have to use the applet on the test. Possible test answers for this one could range from values of, like, let's say, well, you kind of know the answer to this one now. If this was on a test, possible test answers would range in values of 1%, 6%, 17%, 25%. And we probably wouldn't give you the graphic to start. So how would you know that this is going to be 6%, which is a rounded answer for what it is? So how would you know that this right here is 6%? What you would need to do is you would need to say below here, and we might give pictures of the applet too. Sometimes we give pictures. You won't have to use the applet, but so that's 2.5. So that eliminates this answer. So you can't, it has to be more than 2.5. And then the other answer we have to eliminate here. The other answer we would eliminate, or we can eliminate 2 using this, is going to be here and here is 68%. And that leaves 32 on the outside. So, oh wait, no, 16. My brain broke. Yeah, correct. 16 and 1/2. So that eliminates these 2 answers here because they're too big. So we could do something like this right here. How do we reduce standard deviation by half? Oh yeah, let's do that one. So I like that one a lot because you do chapter 10 speedrun, and maybe if randomness, because I want to show you, yeah, chapter 10 is going to be sampling, right? Yep, sampling and then probability, you bet. So we'll do Lydia's question here, and then we'll do a speed run of chapter 10, and then maybe we'll do randomness. And then I'm going to cut these out of the video too and put some like epic speed run of statistics. The voice is too deep right there. I don't want to put, it's got to have the echo, but not the angry noises. So here we go. Yes. This one right here is a little bit interesting. So it's actually easier than it looks. I'm going to do this one in my head. You ready? I can get this one right. This one, I don't know if I can get this one right. I'm going to put 0. I'm going to get that one wrong. Just so everyone can confirm I got this one wrong. Who wants to see the quick trick for... Lydia, do you want to see the super quick way to get this one correct? Like super instantaneous, like we can do it in our head. You're like, how did you do that? And then afterwards you'll be like, oh, that's too easy. As long as I can do math in my head. I think I've got it right now. So I'll get a 50 on this. There we go. Got it right. How did I do that? How did I get here? Little bits. Rick and Morty. How did I do that? Can I get the other one right? The other one's way harder to guess. The other one, I don't know if I could possibly get. 4 decimals? 4 decimals? We got this. I'm going to get this wrong. Okay, if I got that right, that would have been insane, but no. How do you get... It's all I have to know. Okay, so here's how we get here. Let's talk about how we get here. Okay, so let's look at the equation. You ready? And the equation looks like the following for this one. The equation is going to be P times Q over N square root. What do you want right now of this, Lydia? What do you want of this? You want what of this? You want what of this equation? You want what of this equation? What would you like of it? Because you're saying this is my current standard deviation. I'd like it to be what it currently is, like with the second part of this problem. And this is the answer to the first part, P times Q over N square root. I just can't do that one in my head. I mean, I could probably do it. Half of it. So we just want to take half of it, right? Can you take this right here and just put this into here? What would you do to this? We can't just put that into there. How about we do this, though? Well, now it's no longer 1/2, but how about we square it? Does this all make sense, what I've done right here? Is that still 1/2? Like, mathematically, if I square root it and I square it, is that still 1/2? Yes or no right now? Like, don't worry, I'm not trying to play tricks. I mean, that does look crazy right now. But does everyone agree that is still 1/2? Because you can also distribute the square root and put the square roots like this right here, but that's still 1/2. Like Kayla's the math major right here. She confirms, Brian, that is 1/2. We are good to go. If she said no, I'd be like, oh crud. I'd be like, what have I done? So we are fine. 1 squared is 1. And now mathematically, what can we do? Well, now they can combine together. So now we can just go right here and we'll put this, put it down low. So now we can just do this. P times Q, the ones just doesn't matter. And then we do 4N. So what did Brian do in his head? Let's go look at the problem again. What did I do in my head with 172? I took 172 and did what? First, I worked with the 17. I did 17 times 2, and then 34 times 2 is 68. Then I did 2 times 4. So all I did was take 172 and so that's what I was doing right there. That's all I was doing. I was just saying that. Interestingly enough, I do want to point something out. So this is a very interesting concept, Kayla, especially when you talk about like decreasing of confidence intervals, because there's a diminishing return to sample size increase. Because if you want your interval to be half the width, you have to take 4 times the sample. But if you want your interval to be a third of the width, which is an additional question we could ask, like could be on the test. I'm not saying it is. You're like, oh, it's going to be on the test. This is not a hint moment. But if you wanted to get a third of your width of an interval, you'd actually have to take what of your sample? Like if you wanted your interval to be a third of its width, to make your interval, like when we do confidence intervals coming up here in 2-1 and for 320, if you wanted your interval not to be half of its width, which would require 4 times the amount of your sample, if you wanted it to be a third of its width, like 33% of its current size, you would have to take what amount of your sample? It would be this much more of your sample to create via just the width of the interval, a third of the width. So we'd go through the same process right here. A lot of people will say, exactly, Lydia, just that's 50 points right there. Exactly. A lot of people say 9, but it's the same process of doing this right here. If you want a 10th, if you want your interval to be 10% of its original size, if you want your interval to be 10% of its original size, you need to increase your sample size by a factor of 100. So it's really hard to make very, very precise intervals because there's a diminishing return to, this is just statistical theory, like large samples are, like 100's a good sample, and then if you want to get half the width of your interval, you have to get 400 observations. So if you have an interval here and you want to make it half as wide via increasing your sample size, you need 400 observations instead of 100. And if you want it to be, if you want your interval to be the 10th of a size, because you're like, this is a too wide of an interval, we need it to be like 10% of its size, like we need it to be not this, but like that, it would require 100 times your sample size. So you'd have to go from 100 observations to 10,000 observations to mathematically have 10% of the size of your interval. So there's a diminishing return to increasing sample size. So that's why, especially in companies and stuff, you'd figure out the right amount to sample because it's going to cost money to sample. And that's where statistics and business analytics really overlap because it's like, and mathematics. So Kayla, this is like the mathematical side of like, why don't we just go sample twice as many? And it's like, well, we get a diminishing return. If we're sampling 500 people and we want to sample 1,000, we're going to see some decrease to our standard deviation. But I guess what you could do is, what would it do? It'd be square root of 2, right? So that I should know that one. I should know that one. This is classic. You square root 2 all the time in like a lot of disciplines. So you would have 1.414. I know that one. It's classic. Your interval would be 70% of its original width. If you double your sample size, you'll have 70% of the original width. So what that means visually, just last part of this, and then we'll finish the last part of the problem, is if you have an interval like this, here's your interval, whatever 70% of it's going to look like. It doesn't have to stay in the same spot, but your interval is going to be about 70% of its original width. So you're going to decrease the width of it by doubling your sample size, but it's only 70%, like 70% of its original width. So you get a 30% decrease. P times Q over N square root. So, too big. P times Q. P is 0.13. Q is 0.87. That's just the complement. These add up to 1. P times Q over N and square root. Close. I mean, not right, but close. There we go. P times Q. Like I said, I'm not going to get that one. That one's 4 decimal places. I was like, it's going to be about that 0.02 something. And I was, the third and fourth decimal were really hard to guess. Third one, I had a chance at. Fourth one of pure randomness. Second one, I was pretty sure. I was debating 2 or 3, hence I went high 2s. But third one would have been a miracle, and the fourth one would have just been me winning the lottery. So beyond miracles. So yes, with that, I think we should do a speed run. I think is it Dylan? It's D. D, if you're here, I think you wanted a chapter 10 speed run. Let's go. You're welcome, Lydia. Great questions right there. And I like doing the statistical theory side of it sometimes. I can always just answer questions, but I want to, explain and maybe turn it into a test question. Like this one is now like, how would it look on a test? So that way we're not just like, here's the answer to the question. Let's go grab the, let's go grab the from the StatTool website, which they are moving apparently. You bet, Dylan. Is it Dylan? Or I can call you D if you want. I think that'll bring up the StatTool website for those looking for this. I'm going to bring up the review material. We're taking a screenshot of this and bring it over here. Thank you for asking for this because this will help me with doing the review. Chapter 10 sample surveys. Perfect. It's all on one page. Let me screenshot this, bring it over. And we will put this into its own video and everything later. Let me reappear on the screen. Daniel, there you go. Whatever. You have a meeting? Awesome. Enjoy your meeting. Let's see here. We got the speedrun screen here. Let's bring up the speedrun screen. Let's do this. Speedrun screen, go. Wait, where's my new document? What? Let's bring up a new document. Wait, what? It's not bringing up a new document at all. Microsoft Word, you okay? Oh, that's not good. What are you doing, Microsoft Word? There we go. We fixed it. Okay. Whoo, let's do this. Let's do this. Okay. Just getting ready. I'm going to focus here. It's like, okay, this is going to be in a video. I'm going to cut this out. We're going to get a video for this. Good speed run. Got to focus. Got to get that energy going. That energy. Let's make sure the pens are working. Pens are working. We're good to go. Here we go. Put the hair back behind the ear. 3, 2, 1. Okay, when it comes to sample surveys, we need to use our note cards here. Use Quizlet, flashcards, or something, because this chapter is a lot of memorization. When you have things like a population and a sample, we have here the population is every person or thing we want to understand. So think about, you're at the M&M factory and we're creating M&Ms. The population of M&Ms would be every single M&M we create. Now, when you go out and you take a sample, the first thing you're going to do is have a sample frame. Now, the sample frame, which is later on the sheet here, is everything you have access to. So the sample frame is everything you have access to. So maybe you go in, let's say in February, and you're sampling M&Ms. So only the M&Ms created in February could you possibly sample. I think this is where a lot of the confusion is between a population, sample frame, and sample, because the population is all M&Ms, but the sample frame is the ones we could theoretically sample. So we don't actually take everything in the sample frame unless we're doing a census. More on that in a moment. But with this right here, we are looking at everything we could possibly take And this is where we will get our sample. The sample will be the observations, or the M&Ms in this instance, that we actually take. Now, they're probably not all red M&Ms, but we're just marking them red here to denote that these are the sample. So just to review these key concepts, the population is every person or thing you want to understand. Our factory makes M&Ms and we want to understand the M&Ms. The sample frame is the things you have access to sample. Since we are going in February, we only have access to the M&Ms made in February. We can't sample ones made at other times because they're not in the factory, so they're outside of our sampling frame. Now we have the actual sample, which are the M&Ms we take. We're not going to take all the M&Ms, at least in this instance that were made in February. There's going to be M&Ms we don't take. Things in the population and in the sample frame we don't take. Now, things outside of our population cannot be observed. We cannot take a sample outside of our sample frame. So these are things outside of our sample frame. They're still M&Ms. We're still interested in them, but we don't have access to taking them. Now, it's important to know here the difference between a parameter and a statistic. Let's say we want to know whether or not our M&Ms are properly made, like they're chipped or something. So we have M&Ms that are properly made is our parameter of interest. So when you look at what a parameter is going to go with population. Parameters are a characteristic, like an idea, like the percent of M&Ms that are properly made, or the percent of M&Ms that are blue, or maybe the average weight of an M&M. This is something that is true for the population. We often think about parameters like maybe the percent of students that are in-state at the University of Tennessee as things that we actually know. Now, sometimes we don't know the parameter, like maybe we'll never know the true proportion of M&Ms that are properly made at our factory, but that might be something we want to understand. And that understanding is obtained from a statistic, which comes from a sample. This is where I always say PPSS. Population parameters are the things we want to understand for everything, where a sample statistic is how we make inferences, and that's why we call it inferential statistics, into the population. So from this sample right here, we will get an estimate of the truth for all the M&Ms, including the ones in the sample. So we want to understand from the sample, we will get a statistic to estimate the truth for the population of all M&Ms. And that truth is a parameter, sometimes called the parameter of interest. And the key word there is just parameter. Now, what we need to think about is how do we get a representative sample? We need to make sure we go at the right time. We need to make sure we have the right sampling techniques to get a representative sample. And what does a representative sample mean? It means that we are getting the key characteristics of the population and not including bias. Bias is kind of the inverse of representative, where we don't have the characteristics we're looking for because maybe we went during the wrong month. You could say, wait, February is when everyone's on their best at the factory, and we're getting a sample that is actually too good, and we're not covering the other months. More in these biases in a moment right here. But we need to make sure we have a representative sample. Now, one thing I do want to mention here, a very important topic we should know that's not on here, is going to be a census. A census is when you take the whole population. So if you take a census, you would actually need, we'll draw it this way, you would actually need access to everything in the population, and then you would take all observations. So everything would be taken. You'd have access to everything, and then you would take everything. So like the US Census, in theory, should take all observations from the population. So you would have access to everything in the population. Your sample frame would be everything, and then your sample would be everything, and that is a census. So a census, like the US Census, is when we collect data on everything in the population, hence we'd have access to everything, and then to draw this out correctly, we would then take samples of everything. So if we're drawing this out with the colors right here, we would see that we would take every single observation in the population, and they would all be in our sample. So this is a unique thing right here called a census, when you collect data on everything in the population, and thus we would have access to everything in the population. So what are some bad types of sampling? Bad types of sampling would definitely be things like voluntary bias. Now, voluntary bias is when people are going to be excited, or things, which is hard to understand how a thing would be excited to take a survey. More often we think about people giving voluntary bias. But voluntary bias would be like, I use my classic Pokemon Go survey. If I'm like, hey, who wants to take a Pokemon Go survey? And someone's like, hey, I love Pokemon Go. I mean, who doesn't? So if somebody was wanting to take the survey, then that would be voluntary bias. And the issue with voluntary bias is going to be that people are often going to have stronger views when there's a voluntary bias. So when you have voluntary bias right here, which is not a good type of sampling method, you're going to see these people have stronger views and they're not going to be representative of the population. Now, when it comes to convenience sampling, this often is how we do our sampling. I think of convenience sampling as going out and taking the first so many observations. So if you went to a line at Walmart during the release of the new console, let's say the new Nintendo console is coming out, we've already got the new PlayStation, and you've got just this line of people out the door. And so you go and you talk to the first 5 people in the line. If you talk to the first 5 people in the line, you might just like walk up, maybe the news station's there and they're saying, "Hey, are you excited about the launch of the console?" You'd be like, "Wow, everyone's so excited." It's like, well, they talked to the first 5 people in the line, the first 5 people they had access to. Is that really representative of everyone in the line? Is that really representative of everyone who's interested in buying the console? We need to make sure if we want to understand the views of the population, which might be people who play video games, then we need to take a representative sample of people who play video games. And the first 5 people in a line buying a console would not be representative of individuals, all individuals who play video games. So they're kind of going for the easiest people to talk to, and those aren't really the views of the whole population. Now we get to the good types of sampling methods, the ones we should actually do. So we have here simple random sample. With a simple random sample, let's write down the key steps for this. We'll do the steps for each one of these. Simple random sample steps are... Let's go ahead and put these here. Simple random sample. 1, everything in the population gets a number. So we'd number all our M&Ms, and then 2, select these numbers randomly. So the way we do a simple random sample is everything in the population gets a number, and just assign numbers to them, like we have student ID numbers. Then we randomly generate these numbers, and this is a true random way to get a random sample. Okay, simple random sample is great. Next, we have stratified. I'm actually going to go to systematic because these are the easier ones for the moment. So let's go to systematic sampling. So when you do systematic sampling, you start at a random. And the reason we do this is because there might be variation in some way with where we start. So we try to make where we start random. So we start at a random starting point, select every kth observation. And what does kth mean? Well, it could be 5th, it could be 8th, it could be 2nd, technically, even though it's kth. But we're just selecting every so many observations. It's like you're watching the M&Ms coming down a line right here, and you say, I'm going to select every 5th M&M and see if it's chipped or not, and just put it in a bag or put it in a bag for the observers to look at. So every blanked observation will be looked at, and we do this right here and just take our samples systematically. So this is a systematic sample where you just have a system where you select every kth, and usually it would be something like maybe every 20th M&M. Who knows? Just depends on how we choose to set this up. We could go into more detail in other classes on what is a good interval to do your observation in. So now we get to the 2 difficult ones that usually people get confused on. You're like, yes, I want to hear about that cluster and stratified. So let's do cluster first. And when we think about cluster sampling has the first key aspect. Things are randomly put into clusters. This is probably one of the hardest things to satisfy because we need random assignment to clusters. There's no reason. Like you shouldn't say like this is the blank cluster and this is the blank cluster. In my class, we talk about walking into Krispy Kreme and saying, "Give me donuts." And they're like, "What?" And you're like, "Give me a bunch of donuts." And they're like, "What kind?" And you're like, "Just give me donuts." That's what we're talking about right here. They're just going to give you random donuts. Don't distinguish anything difference between the donuts. You walk into the Coca-Cola factory and you say, "Give me Coca-Cola, a bunch of Coca-Cola at one time." And they say, "Here's a 12-pack." And you say, "Thank you." Now notice I did not say anything about that 12-pack. You say you walk into Domino's, you say, "Give me a bunch of slices of pizza." And they say, "What kind of pizza?" You say, I don't want to know what type of pizza. And so it'd be really hard because the slices of pizza, of course, depend on what pizza they come from, but they just give you a box of pizza, which has multiple slices in it. This is a cluster sample right here. Each slice of pizza could be considered its own sample. Maybe you're trying to do a quality control on it, and you're trying to see, do the slices have the right amount of cheese? Are they burnt? All these different things. So you could look at each slice to see the quality of each slice of pizza, and then the pizza is the cluster. So what do we do now that we have things into random clusters, which is a little hard to satisfy? We have here that we go and we randomly take the clusters. And as I always say, perform census on the cluster. After we have our random clusters, we're going to perform a census on the clusters, which means we're going to sample every slice of pizza, which means we're going to drink every can of Coca-Cola. This is an excellent day where we get to eat a full thing of pizza and drink 12-pack of Coca-Cola. But these are cluster samples right here, and we haven't said any difference. We didn't say if it's a pepperoni pizza. We did not say if it's a cheese pizza. We did not say if it's Diet Coke. We're just saying 12-pack of Coke. That's a cluster. So with this right here, I want you to think about what clusters are. Clusters are just taking a whole bunch at once. It does not acknowledge a difference. And that is the key thing we need to think about when we get to stratified here in a second, which is where people usually get confused. Stratified does deal with groups. Stratified sampling. Stratified does deal with groups. Acknowledge a difference in the population. Take your sample randomly with respect to that difference. So we are going to acknowledge a difference in the population. What do I mean by this? There's a difference between diet and regular Coca-Cola. So now we are starting by acknowledging a difference. And then we would say something like our factory makes 80% regular Coca-Cola. So we got 80% regular and we have 20% diet. So 80% regular and 20% diet. With 20% diet, if we take a sample size of 200 observations, so we're going to take a sample of 200 observations, then how many regular cans would we take? 160. How many diet cans would we take? 40. And notice I'm saying cans, because right now we're just doing stratified. We're just acknowledging a difference and then sampling in accordance to that difference. Even though these are groups, we're not taking a whole bunch at one time. I know we're taking 160, but that's just 160 individual cans randomly taken from all the regular cans of Coca-Cola. It goes through the same process of a simple random sample. So you're going to enumerate all the cans. This is not multi-stage. You're just randomly taking the cans via simple random sample. So in this example right here, we're acknowledging a difference that our factory makes regular and our factory makes diet. Then we're sampling in accordance to that difference, where we're saying, well, then to be representative, if we make 80% regular and 20% diet, we need to take 160 regular cans and 40 diet cans in our sample of 200, lest we undercover or overcover certain groups. So when you stratify, you always start by acknowledging a difference. If you were to acknowledge the differences between majors, you would be stratifying. Like if you say there's a difference between psychology and supply chain, you're stratifying. If you say, let's go into classrooms and let's take classrooms as groups of students, then you are doing cluster sampling. Although classrooms are not randomly put together, it's the hardest one to always do with cluster. You're taking a whole bunch at once and sampling everything. Notice how here with clustering, we are taking a whole bunch at once. And if I say, go to a classroom and sample 10 random classrooms and talk to everyone in those classrooms, I've never told you a difference between the classrooms. I'm just saying, take classrooms as whole groups of things and randomly take those classrooms, and those are clusters of students. But if I say, talk to, I think we can go this way, forward in time. But if I say, go to majors and take 20 supply chain majors and 18 psychology majors, and I'm doing the breakdown, I'm acknowledging a difference, and I'm not taking all of one major, because that would not be representative. So remember, when you stratify, you always start by acknowledging a difference and then sample the groups according to that difference. When you cluster sample, you are going to have the groups hopefully randomly put into the clusters, and then you're going to randomly take those clusters and sample everyone in the cluster. This, especially right here, this perform a census on the cluster is always a giveaway that is cluster sampling. Whenever you see like, we're going to get information on everyone in that group, 100% cluster sampling right there. Whenever you see that we're talking about acknowledging a difference to start, like if we say on-campus versus off-campus students, boom, that's stratified, because we're not going to take all on-campus students. That you could cluster sample that way, but that would not be representative. We're going to say, let's take maybe 80% off-campus students, 20% on. We're going to do it by the ratio that is representative to the population. These are some of the hardest ones right here. And multi-stage can go about a million ways, more than a million. It can go infinite ways. When it comes to multi-stage sampling right here, you could say, let's go to the Coca-Cola factory and let's take every fifth pack of Coca-Cola cans, 12 packs of cans. every 5th pack of Coca-Cola cans, like 12 pack, would be a cluster done in a systematic way. We could say, let's go to the Coca-Cola factory and take a certain percentage of 12 packs of regular, a certain percentage of 12 packs of diet. And now the 12 packs are the clusters. And by saying, let's take a percentage of them for each group, we're stratifying because we've acknowledged the difference by saying we need to take diet and regular, but we're going to take 12 packs. The 12 packs are the clusters, and acknowledging the difference between diet and regular is stratifying, saying we need 80% diet 12 packs, or 80% regular 12 packs, and 20% diet 12 packs. There's about a million ways, more than a million ways this could go, but listen for those types and remember your sampling methods. Last but not least, we have the sampling biases right here. When it comes to non-response bias, this is kind of the inverse of voluntary bias. These are all bad things. Non-response bias is going to be when people elect not to respond to your questions. So a lot of times controversial questions are going to be non-response bias. You might call someone up on the phone and they hear what your survey's about and they say, yeah, I don't want to take part in that. So these are when the people who don't respond, or the things we don't get information from, differ in the ways than those who do respond. So this would elicit non-response bias. And just think about what it sounds. These things are not responding, and thus this puts a bias into our survey. Next, we have undercoverage bias. When it comes to undercoverage bias, these are still bad, so maybe I'll still use the light red right there, the pink, to say that these are bad right here. We have when we leave out a certain group or voice in our survey, and thus it is not representative. So if we went to the Coca-Cola factory and we only took regular Coca-Cola, how would we know if the Diet Coca-Cola is doing well? We would undercover it. So if I say, go down to campus and go to freshman intro classes and talk to them about what they think about campus, you'd say, Brian, that undercovers other groups of students who are not freshmen because I'm not going to have access to those students. So just talking to freshmen, which of course we should get their viewpoints, is going to undercover the other class levels of students, and we would not have access to them. So undercoverage means leaving out a certain group or voice unless you do not get a representative survey. Response bias is also bad. When we have response bias, the way the question is worded or the actions of the person giving the question can elicit a certain response. Hence, the bias is in the response. Just think response bias. The bias is in the response. So we think about instances of this where the question is worded in such a way like, do you think it's fair that an 18-year-old can get married, drive a car, go to war, but can't buy a beer? Do you think we should change the drinking age to 18? And thus, do you think we should change? And it doesn't matter whether you agree with that or not. The problem there with the question is the response bias elicited by the way the question is worded, because the question is trying to push people. Someone said, yeah, I think that's fair, or I'm fine with that. But the question's pushing you in a certain way to elicit a response. And that will not then be representative of the views of the population, because we're kind of pushing people towards a bias, maybe towards how we want it to be answered. And everything right here, we've done a very, very kind of short chapter, at least in terms of the idea of what's possible via sampling. If you've ever taken a course on sampling, then you know that there is a lot to consider, and proper sampling is super important to getting good statistics to understand the key characteristics about the populations that we call parameters. And with that, under 20 minutes, whole chapter done, every topic talked about. Keep working hard. We're going to challenge Davey504. He's doing speed runs of base these days. So Davey504, if you want to do some stat speed runs, you're always invited. 20 minutes. Did that help out, Daniel? 20-minute speed run. We've got only a few more. How many more chapters we got left? What other chapters do we have? 20-minute speed run. Gonna drink my second cup of coffee later. That says fall 2000. What the heck? Oh my gosh, I'm losing my mind. We did decision trees. We did sample surveys. Oh, wow, look at this. Ooh, chapter 13 is going to be crazy. We've only got 3 more speed runs. Man, not a lot on this test. 3 more speed runs will be good to go. HDT has got an equation in the chat. They got the variables right there. Be okay for the VIF? I think so. I posted a quick question on the Discord if you have time. Yeah, let's take a look at it here. let's see. Question on the Discord is in the general chat. Wait. There we go. Someone's happy about, yay. I'm going to put a yay next to that. Here we go. General. Here it is. Using the poly function poly1. Let me go over. I'm going to change my view right here. So using the poly function poly1 is the original model. Yes. Since this is for the task 2, should I only discuss poly2? Task 3 asks for check regression of these variables in their non-transformed state. So it's actually like the fit of the model. Like it'll still check the fit of the poly model. So you can just think of it as like the fit of it. This is fine right here. It's fine. This is great output. There seems to be an issue with the fit for poly 2 of AVG temp and poly 1 for AVG humidity also equals spread and normality. These don't look that low. I'm guessing the plots look okay-ish. So those don't look that low. The plots probably look okay. I think we did the, we're gonna head, let me see what time we got class. We could do the bank loan one, Jesse. If you're hanging around for a moment, we'll do the bank loan one here. Also, how do I use choose order? I have the fine transformation choose order doesn't show the power to raise X and Y to. I'll show the choose order, and then, does that make sense, Kayla? And then Jesse, if you hang around, we will do that question. Let me head over to the main screen here. And yep. Oh yeah, so should we do that? What should we do? Let's take a vote. Let's go to the main screen. Awesome, Jesse. We'll do the bank loan question here. So if we have a model like this right here, you need a simple linear model to do the choose order. And here is the choose order function. And there's a lot of ways to do this. We'll have some heuristics, like ways of doing stuff. But here's the choose order. And definitely check out, feel free to ask more questions if you have it. This is the choose order. It takes a simple linear function and looks for higher order polynomials. And going off of this right here, you want your R squared adjusted to be what, or HDT? You want your R squared adjusted to be what, or? You always want your R squared adjusted to be higher or lower. It'll always be lower than R squared. It'll always be lower than R squared. But you want it to be as high as it can possibly be. So the R squared adjusted right here is, the best one is this one. The second best is this, and the third best is this. But they're all pretty close. And Dr. Akaike's information criteria, which is AIC, is actually the best here. This is how close our model is to the truth. Very famous statistician. Japan gave him like the highest possible honors. Like, man, I wish I would have met him. He was a mentor to Dr. Humphreys Bosdogan, who's in our department. I wish I could have somehow said, Dr. Bosdogan, you're going to this conference and Dr. Akaike will be there. Can I go and say hi and be like, your work is awesome. Thank you. And then I'll be like, nice meeting you. You would change the world of statistics with this. So the best one is the lowest one, and I would pick this right here. If you look, all of these higher order polynomials look to be basically derivative of the second order polynomial, and we definitely go over yesterday, and feel free to ask. But we did this also yesterday, which is always interesting to look at. I just like making crazy graphics. And if you look at this right here, it really looks like it's just a polynomial. Like, these are overfit models. We're going to way high of a polynomial degree. Like, this is ridiculous. You're overfitting. We have ways to tell if we're overfitting later, but this model right here is too low bias, too high variance. More on that in 474. And yeah, everything looks to be just the polynomials flowing through here. So I would say the polynomial model is going to be our best bet for this one. And we probably would see this still in the AIC. Yeah, the minimum AIC is this one. So we're really, even though R squared adjusted is going up. Ooh, that's interesting. I should talk to Dr. Petrie about this and see what he thinks, because I do not think we should be going to that high of a polynomial model unless there's some sort of, it's not time series, but I don't know. I should talk to Dr. Petrie about that and see if he revises his ideas, because he might have a slightly different view by his heuristic that he uses. So I would say, yeah, look at this. Would you rather just use AIC here? And he might be like, yeah, let's use AIC. Brian, you're not supposed to fit a 20-order polynomial. What are you doing? And I say, I don't know. I'll break all the rules. Let's do the bank loan problem here. Let us do the bank loan problem. Let's see, where's that bank loan problem? It is believed that a certain percentage of children are nearsighted. Aha. Here we go, Jesse. Let's do this. Bank loan problem loading up. And let's take a look at the bank loan problem. So, oh, awesome. That's where everyone's getting stuck. Oh, did I not have it up anymore? That's where everyone's getting stuck on the last question here. So the first parts, we'll do it maybe a little quicker today, but we'll explain each part of this. So the z-score part is messing you up. So you actually, you know what's really interesting? You don't have to get a z-score. But we will get the z-score just to check, but you can actually do it without getting the z-score. So the mean for the distribution of the sample proportion, we should know these equations. Let's go ahead and take a screenshot of this, and let's write in the equations for this. These are straight out of the notes. And so the notes for the equations for this are going to be, let's just go ahead and put this in here. So we've got the mean for the distribution of the sample proportion, and we covered this in an earlier question today, and we went into great detail about how and why we use this, but this is just going to be P, and this is P. So we're good on that. We also need to know, once we find P, instantaneously you should find Q. If you know what P is, we're going to find Q. They are complements. Notice that the two of these add up to 1. Always remember that. Do not worry if you ever have to ask it. You'll say, oh, I knew that. I knew it, Brian. I say, I know you knew it. We're just practicing. That is the sample size right there, and this is really going to help when we get down here to this one, which is P times Q over n square root. You'll hear me say that 100 times. P times Q over n square root. So we'll find the bottom one here. P is 0.11. We're just plugging these numbers in. P times Q over n square root. There we go. We got it. Let's go back to our question, and let's put in the mean. So the mean is going to be 0.11. And just to explain briefly what that means, what the mean means, is to say if 11% of people don't make their bank loan payments on time, then if we give out loans, I'd expect 11% of people to not make their bank loan payments on time. But it won't be exactly 11%. There'll be variation around it, and the variation is described by the standard deviation. So MuBot's going to help us out. If you're watching this, look over at the chat, because MuBot is putting in the David M. Lane applet. So we're going to click the link once MuBot does that. MuBot. What do we pay you for, MuBot? This is saying down here on the bottom, what is the probability in a sample? We would see 12%. And so we can always take a guess. I love taking guesses on these. We get 2 guesses, and then we have to be serious. So I've got a decent guess on this one. I might be able to get it. I've got a decent guess. Oh, it's close. My brain's breaking. This is a tough one. This is a tough one. I'll take one guess. This one is very hard to guess. If I got this, it's a miracle. Nope. So let's see. Let's look at the answer right here and see how it's found. That was just a guess. We're going to put here the mean and the standard deviation, and then we're going to go above 12%. And I will know better when I got this. Oh, it's 26%. I was close. 26.1 should be the answer. And there we go right there. I was close. I said 27. So close. It's hard when it's that close to the center because the numbers are a lot. They change quickly in that area. So we got a decent guess in on it. I was able to think about the z-score of it. Yeah, I was close. I was hoping I'd get it. I was like, within 1% I'll take, but it's close. What I was doing is I was finding the z-score. So let's think about how Brian is finding the z-score for this. The z-score is found the following way. Using our curve, and let's go grab the curve, we need to take observation minus mean over standard deviation. Observation minus mean over standard deviation to find the z-score. So we're going to put this down here. And the z-score should be between what and what? 0 and 1. So 0, 1, 2, 3, -1, -2, -3. Like we can see this visually right here, and we should hopefully be able to draw this, that the z-score is going to be between 0 and 1. So we need to do the observation of 0.12 minus the mean, because remember, this is our observation right here. P hat is equal to 0.12. P is equal to 0.11. and we're doing observation minus mean over standard deviation. Boop. And p times q over n square root. That's the z-score. And here we are with this. Observation minus mean, and the standard deviation was, it was like, I think it rounded to that. So we have, there it is, p hat minus p over this, and it's 0.639. So hopefully finding the z-score, does that make sense how to find the z-score right here, Jesse? Does this all make sense? I carried more decimals when I did it here, but does this make sense how to find the z-score? I'm clicking it. I played a lot of Mario Party, and clicking this is harder than playing Mario Party. Does it make sense how I found the z-score of positive 6.39? I take observation minus mean over standard deviation, and that's where this is right here. Like this point right here is 0.639 standard deviations above the mean. Milton Scholar question. Let's talk about that next. And so what I'm actually doing, the reason I'm able to guess this decently, I'll explain why, is because people was like, how do you do that? I've done a lot of these problems. That's how that helps. So what we're looking for is we are looking for this area. And this is the answer to our question. So this is, if you use the z-score, this is the answer to the question. So what I did was I took a number I know. I was thinking it was about 0.6 something. I was like, it's like 0.6. Like I was trying to divide this in my head and I was getting 0.6 something. And then I took the number I know as a z-score, which you don't have to know, which is this. And watch, this will be 25%. So using this, which is almost exactly 25%, there's more decimals. There we go. Now it's 25%. So I knew 0.674 is 25%. So I said, this has to be a little bit more than 25%. So I was like, it's very close to that, but it's a little bit more. So instead of doing 25%, I did a little bit more than 25% because I knew the answer of, and I need to memorize this more. There we go. 0.6744. We did that one earlier, Ben. We might hop off here in a moment. Check out earlier in the stream. We did a full-fledged example of it. We took like 15, 20 minutes. I can do it again tomorrow. I might hop off a little bit here because I'm going to answer emails between class and office hours. But check out, I think it was 8 minutes into the stream or 10 minutes into the stream, we did it. So check out that one. We did the newspaper one. We did a full walkthrough of it, explaining all the details. So you can also like fast forward through while watching it if you want. If you're like, wait, what part? So you'll be able to. You're welcome, Ben. You're welcome, Ben. And if you're stuck on it tomorrow, because it is due tomorrow, please hop in and be like, hey, Brian, do the newspaper one again. Explain it again. But we will do that. So yeah, you got it. And I think HDT had questions about the Milton Scholar. And thank you, everybody. Let me throw some 100 points for positivity. I'm glad no one's ever like, what? You won't do it again? I'm like, no, it. What? For Milton Scholars, should I just wait for the interview you might have with a former Milton Scholar? Should I would contact Dr. Petrie. You're welcome, Daniel, right there, anytime. And we got a speed run in today. You're always welcome to contact Dr. Petrie. Let me do this. You're welcome, Daniel. Like, we'll try to do more. Hopefully we can get another one in tomorrow, and then maybe I'll film some, because I know tomorrow's don't worry, I want people to hop in and ask questions. Hopefully we can get another one in tomorrow. And then we just have 3 more to go. Randomness is kind of hard to make a speed run on because it's such a, like, there's just understand how to do simulations mostly. That's a really big thing. You know what we should do, Daniel? What if we did one more speed run today? What if we do the randomness and knock that out of the park? We get that done. Then we just have probability in chapter 13, which that one's gonna be like a 30-minute speed run. It's not a small chapter. Chapter 13 is a whole week long. So let's see here. Let's knock out one more speed run here. Let's do it. And then I'm gonna cut these up, put them into videos. Understand what randomness means. Simulation. Gosh, this is like the shortest thing ever for like a review. What kind of review is this? Understand what random means. Oh my gosh. What kind of speedrun is this? I think if I hit the speedrun button, it'll do it now. I was going to open a new timer. I already opened the new timer. Okay, I'm on the speedrun screen. I'm just getting everything oriented now. Okay. Let's open a new screen right here. Okay. There we go. I agree. I know, let's do this. Okay. Get everything ready. Get hair out of the face. Just get that burst of coffee through you. Got this. Coffee. Gonna get second cup of coffee here in a little bit. Let's do this. Here we go. Speedruns live. That's what we do. Okay. I'm listening to the epic speedruns. I want to make a new intro too, Dylan, with the epic. I'm thinking about it like a heartbeat, where it's like epic speedruns of statistics. Brian Stevens, and then I'm gonna use the same thing, but like epic speedruns of statistics. If you watch Epic Rap Battles of History, they do like a different thing, and so it'll be like a heartbeat, and it'll like be like going towards the screen and going further. And yeah, that's my like idea of what to do for this one. That intro scene took like 3-4 hours to make, but I think I could edit it and change the colors because I've already got all the stuff I've created, the resources to like redo it. But I don't know. I was so happy with that I don't know. Anyways, let's get serious here. So we'll make a fun one there. I just need to find a heartbeat thing and like raise the volume as it gets closer. And yeah. Serious face. There we go. I gotta make a new one for test 3. When it comes to randomness, there's a lot to talk about here with just 2 things on the review. What does randomness mean? Now, randomness is something statisticians use as a tool. That's important to understand right there. We love randomness. You knew it was gonna happen. So when it comes to randomness, we use it as a tool to do 2 things. 1, take random samples. And we talk about this in other chapters where we can take random samples and we can use randomness. Randomly select individuals in the population by numbering all individuals and then selecting them randomly is a simple random sample. So we love randomness for this. We can also perform simulations. Now, what is a simulation? A simulation is a way of taking a real-world event and using randomness to generate it. And we see this all the time, especially in video games. You may have heard the term RNG. RNG stands for random number generation. Now, we don't put that on the test, but it is something we see all the time, especially if you play video games. Maybe you're trying to get a special item in a video game and it has a 1 in 1,000 chance of appearing, and it's RNG whether or not you get that item. What the video game is doing in the background is it has a list of numbers. It has numbers maybe 0 through 999. Why would it be 0 through 999? Well, a lot of times when we use random number generation, we might want to use 3-digit numbers. So with 3-digit numbers right here, 00 through 99999, you can do 3-digit random number generation, and you actually have 1,000 numbers. So using these random numbers right here, we could actually simulate getting an item in a video game. Now, this would actually be a lot to simulate right here, but let's do our own simulation with something a lot smaller. Let's say you want to play scratch-off tickets. Now, always gamble at your own risk, but a lot of times we like to use things like lottery and probability to talk about simulations right here. And let's see. If you have a 20% chance of winning on a scratch-off ticket, then how could we use random numbers to generate lottery tickets to see if you win on a scratch-off ticket? Well, first off, we need to choose our random numbers. Let's use 0 through 9. If you notice, these are 10 numbers. Just think about these as 1 through 10, but moved over one direction. So 0 through 9 is the same as 1 through 10. And the reason we use this is because it's 1 digit. Think of 0 as the 10. That helps too. 1 through 9, and then you got 0, which is the 10th number. We just have 1 digit random number generation. Now, as I said, for the rules of this simulation, which I am creating, we're going to have a 20% chance of winning the lottery or winning on a scratch-off ticket. So let's choose 2 numbers. And usually we start at the beginning, like 0 and 1, and call them winners. So 0 and 1 is going to be winners, and 2 through 9 is going to be losers. It means we don't win on the lottery ticket. Now, when you think about this, the way the simulation is created, and listen to this very carefully, the way the simulation is created is we have a 20% chance of winning with any random number that is generated here. So the way the simulation is created, there's a 20% chance of winning. Now, let's say the simulation questions on the test, and this is just an example of the many, many types of test questions we could write. Let's say the simulation question asks, You go out, and we'll write it out here. That'll help. You go to the store and buy 5 scratch-off tickets. Use the 4 trials below of this to see what is the probability they're all losers. So in this simulation, you have a 20% chance of winning. You are going to go to the store and buy 5 scratch-off tickets and use the 4 trials of this. So there's going to be 20 scratch-off tickets bought in 5 clusters each to see what is the probability they are all losers. Be very careful to notice here that we have the probability of all losers is what we're looking at, not that the probability of losing. So let's look at a random number sequence being generated for us right here. These are random numbers. I do want to point out these are not random numbers. I am coming up with these off the top of my head. These are not random numbers. Humans are not good random number generators. If you want to generate random numbers, you need to use random number tables, computers, random number generators such as dice, or many, many different ways like dice, coins, something that can generate randomness. And computers are pretty good at generating randomness. We usually think of computers these days as pseudo-random number generators, as in they are good enough, but we do acknowledge that computers are created by humans, and humans are doing their best to be random, which is pretty hard to do. So we would need a real random number generation for this to be a real problem, but we'll use the numbers here and assume that these are random numbers. When we look at this, we immediately want to start converting these into winners and losers. And remember, our table up here is going to help us out on knowing whether or not things are winners or losers. So let's take a look at the following, and let's use green for winners and red for losers. Actually, let's use yellow, that might help out, for winners. So we have a winner here, winner here, winner here, and winner here. Now, the important thing to know about this question is we're not concerned with how many winners there are. We're just concerned with, were they all losers? And so hopefully right now you're figuring out the probability and what this question would want for an answer. The way this question is worded right now, what answer would we get for this? We've done 4 simulations below where we buy 5 lottery tickets. What is the probability that they're all losers? Taking a look at this right here with this small simulation, we would see one of the simulations right here. The other simulations have at least one winner. So in this example, the probability is 1 over 4. Only 25% of the time, at least via this simulation, which is an estimate of what would occur, would we see all losers. And so this is not going to be proof of it. It's just a very small simulation to estimate the probability of all losers. There's many, many ways to do simulations, and we use simulations to look at real-world events like buying lottery tickets or basketball games or flight simulators. All different things can be simulated. Statisticians use randomness as a tool. Practice the chapter, practice the homework, and good luck on the test. Yay! Woo! 1 more down, 2 more to go. Yay! I don't know if anyone's still here. Let's put on some music. Let's hop to space. Put on one of my favorite songs, relaxing music. We're going to get some more coffee here. That's what I'm excited about. Oh, I have coffee. No joke. I have coffee. Now I don't have coffee. No more coffee. I'll have more coffee here soon. Ran out of cream and I'm using oat milk. Sad day. Sad day. With that, everybody, great job today. Great office hours today. We got 2 speed runs done. We got 4 or 5 stat to 1 questions done. We got some 320 done. We talked about some Milton Scholars. Really awesome office hours. Hard to believe, 80 minutes. So much done. But we will be back next class, BAS 320, in 30 minutes. With that, everyone, we will be back tomorrow. Always bring those questions, any questions you have. I'll see everybody later. Bye for now. Bye. See everybody later.